lecture on liquefaction-induced settlement and indices, and then we'll be back on schedule for starting at 0800 tomorrow. Liquefaction effects are the thing we're focusing on. It's one thing when liquefaction takes your ride. Some people are very in love with cars, so that's a personal thing. It's another thing when it takes your throne. All kidding aside, this reminded me that liquefaction is clearly a flood event. You can see the ring here. So these people's rugs, their floors, the books they left on the floor got flooded. And so it was very mentally challenging to live in homes that liquefied in the Darfield earthquake in 2010, re-liquefied when they reoccupied their homes after fixing them on 22 February 2011, re-liquefied in the June 13 earthquake, re-liquefied, some of these sites liquefied 4 or 5 times. The population of Christchurch decreased because people got tired of these little liquefaction flood events, especially when they damaged their homes, as shown here. What I'm talking about in today's last lecture is free field settlement, and a good indicator of that is in Arasu in Japan for the 2011 Tohoku earthquake, magnitude 9.1, where this building was on deep foundations, where the neutral plane was well below the liquefiable layer. All indications by Professor Tokimatsu is this did not move. And so they fill the hydraulic fill of this made island, liquefied, reconsolidated, and settled 30 centimeters. That's the free field liquefaction we're looking at in this talk. The primary procedure for doing this is the work by Ishihara Yoshimi in 1992. He did very careful laboratory testing, and Professor Ishihara, working with him, were insightful in saying, let's don't just present results in laboratory tests. Let's look at tests in terms of the factor of safety against liquefaction triggering. So they stopped some tests short of liquefaction. Then they ran some tests that they stopped right at liquefaction, and other ones where they basically had low factors of safety. And they recognized in terms of the post-liquefaction volumetric strain, it was a function of the demand increasing as the factor of safety against liquefaction triggering decreases, and the relative density of the soil. If you have a factor of safety of liquefaction of 0.8 and a relative density of 60%, your volumetric strain would be 3%. That 3% volumetric strain, as a decimal, 0.03 times the thickness of the layer, we give you the settlement of that one layer, and you just sum that up. In an effort to make this more practical, Professor Ishihara gives you equivalent blow counts in QC1N. Do not use them. The primary data for the lab test was relative density. There are better correlations than the ones he used many years ago. So use your best estimate of relative density, for example, a modern CPT-based estimate, to get your relative density. And the procedure is pretty straightforward. One thing that's interesting is, for most cases where you have liquefaction, I know the post-liquefaction volumetric strain typically is going to be 2 to 4%. So without much, I kind of already know roughly 2 to 4% for most cases. There are other procedures, just like Zangedal 2004 based their work on Ishihara Yoshimi's work of shear strain. They also took their plots of volumetric strain, which I just showed you, and they estimated a method that way. Idris and Boulanger did the same thing. So I put an asterisk next to them, because they're not really independent. they're based on the same clean sand data that Ishihara developed. And truly independent data set is that based on, that's the basis for the Chetan et al. Procedure, which is based on the laboratory testing of Wu 2002. So you can look at that as being a totally independent assessment. All of this testing is on clean sands. So when you have sands with fines, I think you just have to take the clean sand equivalent to enter these graphs and realize that that is based on judgment and not based on laboratory testing. There are cases where you have non-saturated soils or unsaturated soils, or partially saturated soils that undergo volumetric compression as a result of earthquake shaking. This happened in the Northridge earthquake in 1994. I worked with John Stewart at the time and Daniel Wang on this problem. It did not kill anybody, but there were many subdivisions where just 10 to 20 centimeters of movement, especially houses that were on the cut, fill contact. So the fill settles and the cut does not. That led to property damages that when you summed up $100,000 here, $200,000 here, fixing foundations of buildings like this, it added up to multi-million-dollar lawsuits. In fact, I made some good money as a legal expert on lawsuits that involved over $100 million in claims. And that was just for one housing subdivision. Their method is described in Professor Kramer's textbook. It's described in their paper. But I found that it's nice to divide it into these 9 steps. This was done in the old days, so they could care less about your units. You have to do things in things like tons per square foot. You have to do these correlations the way they're doing it. You have to calculate mean effective stress as 0.65 of the vertical effective stress. You have to do the clean sand correction this way because that's the way they did it. And even though there are deficiencies to these steps, until someone develops a new method, you have to do it their way. The figures are given, and you can enter these figures and walk through that. People have set up spreadsheets, but I think it's good to have these figures in the spreadsheet so that you can mentally see about what the answer would be before you calculate it. After doing all these calculations and going through this procedure, at the very end, you realize that everything is based on one-dimensional shaking. And so they take the volumetric strain for each layer for one-dimensional shaking from steps 1 through 7, and they multiply it by a magical number 2 to get the volumetric strain for bidirectional shaking. That was based on some limited testing. It obviously is not that simple, but that's what you do for now to get in the ballpark. One of the most important things we learned is as we move to real soils, so well-graded soils, soils with fines, the kinds of soils you actually use in California and around the world to do field jobs, is relative density is nice for clean sands, but for relative compaction, so the dry unit weight that you compact the soil to divided by the maximum dry unit weight achievable by the modified product of tests, you can see the importance of relative compaction. These siltier, sandier soils that have high relative compaction with the same shear strain demand undergo less volumetric strain than the soils that are not as well compacted. So obviously, compaction is important. What's also interesting is if you look at a clayier soil, so this soil has plastic fines, all these soils have about the same relative compaction. See the difference in the volumetric strain at this shear strain to saturation. When you compact dry of the line of optimums, you tend to have a more unstable soil structure, and from either water coming in and hydrocompression or seismic shaking and the shear strains produced by them, you get more volumetric strain when you compact dry of the line of optimums and you get less when you compact wet. I'm a big believer in doing a dry unit weight versus water content, looking at it in terms of the maximum of the compaction curve by the modified Proctor and the standard Proctor, drawing a line and always making sure I compact wet of the line of optimums. When you compact dry of the line of optimums, you are potentially having time bombs when it comes to water coming in and causing hydrocompression, or an earthquake causing cyclically induced volumetric strain and then settlement. For capturing liquefaction-induced ground damage, one of the most famous papers and charts is from the Ishihara 1985 state-of-the-art lecture he presented in San Francisco for the International Soil Mechanics Conference, where he looked and said, I can relate this by the thickness of the crust, the non-liquefiable crust, and the thickness of the liquefiable crust. If I have a ground motion PGA of 0.2 G, because of course it's going to shift to the right for higher intensity motions, but for a ground motion of 0.2 G, the difference between observing liquefaction-induced ground damage and no liquefaction-induced ground damage is principally the thickness of the crust. As the crust gets up to 3 meters, you do not see, or is greater than 3 meters, you do not see liquefaction-induced land damage for the case with PGA's 0.3. This worked out pretty well for Christchurch to a point. It's actually based on just a couple of case histories and can be improved with additional case histories. One major caveat, this is only for level ground away from a free face. If you've got slightly sloping ground, gravity is always working and the ground will move and you can get a lot of disruption of the surface. We do liquefaction triggered analysis, and we often look at data in terms of the raw data, I sub C, the cyclic stress ratio versus the resistance, calculate factors of safety. It's useful to look at it this way and see zones that are going to liquefy in red, zones that are not going to liquefy in green, to get a sense of how extensive the liquefaction might be for the design ground motion. Then the next step, after looking at triggering, is starting at the bottom and using something like the Zhang et al. 2002 procedure to estimate the post-liquefaction volumetric strain as an index of how much the ground will settle in the free field, but also how much damage. These are all CPTs done at the same site. These only got down to about 8 meters. These got down to the stiff material at depth. And so you could just translate these over and realize they're essentially saying the upper soils are about the same. These obviously are not characterizing the lower soils. But this is a case where things are relatively uniform in terms of liquefying and contributing to settlement. Sometimes you'll see something that looks more like this, and you realize that's the layer. So I like looking at the accumulation of volumetric strain that leads to settlement as you go up through a profile to see where the key layers are. In terms of trying to capture this, we have liquefaction potential index, we have liquefaction severity number, we have a number of other methods. This is probably the most popular because it's the oldest, but it's based on factor of safety. And factor of safety is not as useful as volumetric strain, as I'll show you. Also, the weighting scheme is linearly increasing with depth. This one is 1 over Z, so it really weights the shallow liquefaction. And it's the shallow liquefaction that causes more ground damage. Taking Ishihara's plot and flipping it, you see that as I get a decreasing factor of safety for liquefaction, as the peak ground acceleration increases, I will get an increasing volumetric strain as this decreases and as my relative density decreases. So looking at volumetric strain goes beyond looking at factor of safety. I could have a factor of safety of 0.6 and a relative density of 70% doesn't lead to as much damage as a relative density of 40%. So volumetric strain is more informative than just factor of safety. If we do a one-to-one comparison between LPI, which is just based on factor of safety with the linear weighting, we get these dotted lines for a cone that's representative in the red district with a lot of damage, the red zone, an area that's had some damage, and then some limited damage. With LSN, because it considers you can get some damage with a factor of safety slightly greater than 1, it has a limiting volumetric strain, which makes sense. Once you get liquefaction, if you have higher acceleration, you don't really get that much damage. Now, loose soil liquefies and you have problems. If the acceleration is a little higher than that, it still liquefies and you get damage. So this is physically makes more sense. It's affected by relative density. We know everything's affected by relative density. And as I mentioned, it weights the shallow layers more. So I see an improvement with LSN. It's informative to look at how ground failure, as evidenced by high LSN numbers, changes as the peak ground acceleration changes. Nothing happens, and then you cross this threshold and you go from not so bad to really bad over a small change in acceleration. Liquefaction is a brittle event. So this is the LSN as calculated for Christchurch. This is the observations, and as I mentioned, it does a pretty good job. It doesn't do a good job on the silty soils, but that's because our triggering methods don't do a good job. If our triggering methods don't do a good job, then our volumetric strain estimates are going to be off, and we're going to overestimate damage with LSN or any technique that's based on a factor of safety of liquefaction triggering. And again, we know why that's true. We talked about that. That's largely because we're missing the soil stratigraphy at these highly stratified sites in the swampy areas. And the way to look at that is start looking at system response, as I talked about. If you want to estimate how a football field is going to settle, these are the methods you can use. We're talking about post-liquefaction, free field, settlement. If you want to understand how a building settles, do not do what some practitioners have done. They take a CPT on one side of the building, they take a CPT on the other side of the building, they use this plot to calculate post-liquefaction volumetric strain in each layer. They add that all up and they say, well, this will settle 30 centimeters, this will settle 10 centimeters, so I'll have 20 centimeters of differential settlement. No, this is only 1D settlement due to post-liquefaction volumetric recompression. There's nothing about shear-induced settlement, therefore it cannot estimate building settlement, because building settlement includes shear-induced deformation as well as post-liquefaction volumetric settlement. So tomorrow we'll talk about not the free field settlement, which is 300 millimeters here. We'll talk about this building, which is on a mat. It's 3 stories. It punched in to the liquefied crust 400 millimeters. The liquefied crust went down 300 millimeters, so the total settlement of this building is 700 millimeters. It's how much the free field settlement went down, and it's how much this building pushed into that soil because of the shear-induced settlement, which is often larger, as shown here. Have a good night.
Thank you.
If you have any questions, we can answer them, but if people are tired, up and talk to me and talk to Professor Kramer. We'll hang around for a little while. Thank you.
Thank you.